Thanks for that introduction. So I'm Matthew Treinish. I'm a software engineer at IBM Research, and I work on the quantum computing team there. Today I'm going to be talking about quantum computing and open source software's role in the developing field. Before we can get started, though, we need to really talk about what a quantum computer is, because I don't think most people actually know. If you read the tech press, you probably have something like this. Which is, oh my God, my RSA is going to be broken, the world's on fire, we have no secure communication anymore. And that's because of a theoretical algorithm that came out in the 90s called Shor's algorithm, which allows for efficient factoring of prime numbers. But what the tech press and most people I've talked to this week so far aren't really well informed on is that Shor's algorithm depends on a universal fault-tolerant quantum computer, which is still a long ways away. The devices that exist today are very noisy and have lots of errors. But another common thing I come across, and what was my personal view of what a quantum computer was, comes from science fiction. This is what I hoped a quantum computer looked like when I started working on this field. This is from an anime I like, Gundam 00. This was the quantum computing there that housed the super smart AI that tried to bring world peace. I like it because people are in space and it glows. But a real quantum computer actually looks like this. This is one of the quantum computers at IBM Research in Yorktown Heights, New York. And most of the space is actually taken up by cooling. That white cylinder and all of the gold bits are what's called a dilution refrigerator. And that gets the temperature inside down to about 10 to 20 millikelvin. So really, really cold, colder than outer space pretty much. And that's basically what all the space is. You can see a little bit in that picture in the upper right-hand corner where you can see the cables for the transmission lines to send the microwave pulses down to the chip to control it. But most of it is cooling. And that's because these devices are very sensitive to noise. And any source of heat or RF or anything is entropy in the system, which will contribute to noise in the quantum computer. The actual quantum chip is very small, just like in a classical computer. The microprocessor is the smallest bit in the laptop. And that's just some guy holding one. If we zoom in on one of those, these are some dye photos of the quantum chips. These are two publicly accessible quantum computers that IBM produces. The one on the left is named Melbourne, which is the one hopefully I'll be able to run something on later today. And the one on the right is called Tenerife. And the one on the left is 14 qubits, and the one on the right is 5. And you can see some basic features on these dye photos. The things that are labeled Q, those big dark squares, those are the actual qubits. They're constructed with something called a Josephson junction. You can look up what that is because I'm not going to get into the details. But that's basically what functions as the qubit. And then between the qubits, you see those things labeled B. Those are resonators that allow for coupling between qubits for multi-qubit operation. And then you have other resonators that go out, which are for reading data out and sending signals in to the qubits. And while all of these devices are very sophisticated and pretty cool, there's still a lot of limitations with them. The biggest thing is noise. Even with that fancy dilution refrigerator, these devices are very susceptible to noise. And the longer you run operations on it, the longer you accumulate noise. So that leads to things like decoherence, where you can only run a certain number of operations on a qubit before it loses its quantum state and you just get random noise as your output. There are other things like the number of qubits. This is 14, this is 5. Could you imagine if you only had a 5-bit computer and you could only run operations for like 50 microseconds before it broke apart and you couldn't use it anymore? So these devices still have a lot of limitations. But why am I talking about this then, if there are all these limitations? And that's because it's actually a really exciting time in the field of quantum computing. And to just give some perspective, I thought putting this timeline up, showing some of the key events from the history of quantum computing would be useful. I borrowed this slide from a colleague, so I don't pretend to understand the significance of each point, but it's useful for outlining the broader trends in the history of quantum computing. So you can see in the 30s, there was the theoretical underpinnings of quantum mechanics. And then in the 1970s into the early 80s, there was the theory of quantum information, basically using quantum mechanics to store information and perform computation on it. And it was mainly theoretical into the 80s, into the early 90s, where you had algorithms being developed with this new field. You had conferences on the topic. And then in labs, they started being able to replicate this theory and start building qubits in the 90s. Small single qubit systems that lasted fractions of the time they last today. And it was the domain of being in the lab up until a few years ago, when IBM decided to take one of the machines they had built, a 5-qubit device in the lab, and open it up to the world. They put it behind a public API, let anyone sign up for credentials and submit programs to this quantum computer. And that really changed it, because now it's generally accessible to all of us. Before, you would need basically a PhD and a job where you could work in a lab where you could afford a dilution refrigerator and have a supply of liquid helium to keep it cool. And now you can, sit on your laptop anywhere in the world and submit a job to a quantum computer and experiment with these devices as they're becoming more sophisticated. And that's really where the role of open source started to come in, and where the project I work in came in, because with open access, you needed a tool to be able to program it. Yes, there's an API, but how do you, write an efficient quantum program for it? And that's where the project I work on comes in, which is called QuizKit. QuizKit is specifically an SDK designed to work with noisy intermediate scale quantum computers, which is basically just a catch-all term that says for devices around today, moving into the future with, small number of qubits where there's still noise, there's no fault tolerance. You can't, basically not the theoretical perfect quantum computer, but the real world devices that exist today and for the near future. This toolkit is licensed under Apache 2. And we wrote it to be back-end agnostic, which means it can run on any quantum device or simulator out there. We include batteries with it, so you can run it on IBM Q devices because it's being developed at IBM, but also with local simulators if you don't want to submit your jobs to an actual device. You can just run it locally with the simulator. And like a lot of open source projects, it's built up of components. And we decided to name the elements, or the components of QuizKit after the classical elements. The one we're going to be spending most of the time on in this talk is called Terra, which is the base layer and provides the interface between the hardware and software. Then there's the air element, which is the high-performance C++ simulator that also allows for noise modeling. The aqua element is basically for algorithms. It provides a library interface in Python. So if you don't want to deal with the low-level programming of a quantum computer, it basically gives you a function here. You can run this quantum algorithm, give me the inputs, I'll give you the output. And then there's Ignis, which has not been released yet, but it's for dealing with noise and errors. But as I said, we're going to be concentrating on Terra. And Terra is the base layer. It provides the software interface between the quantum computers and any end user who wants to write a program with it. You can kind of think of it like a combination of an ISA and a compiler, because it provides both the APIs for building quantum programs and also the tools to build those quantum programs for a specific backend, whether that be a simulator or an actual device. And this is written all in Python, which is great for me because I'm a big fan of programming in Python. And it was at this point in the presentation I wanted to show you an example of how you would actually use Terra to solve a real problem, or a hypothetical problem at least. But before I could do that, I thought it was important to give some background on quantum information from a high level. I'm not pretending this is going to be an exhaustive primer on quantum information, and I hope it's not too complex. I'll have some links to more information at the end because I'm not covering every aspect of it, but just to give a feel for how you can use a quantum computer from a theoretical standpoint. And to start, we need to talk about the qubit, or the quantum bit. The easiest way to think about a quantum bit or a qubit is using the block sphere, which is that sphere on the right. you can think of the state of the qubit as being any point along the surface of that sphere. And when you perform operations on a qubit, you're basically moving the vector, which is represented by that orange line, around the surface of the qubit. Just like a classical bit, you can have a 0 state, which is the arrow pointing up, and a 1 state, the arrow pointing down. You don't have to worry too much about that notation. That's called Braket or Dirac notation, and that just means it's a vector. And when you have a qubit, you can have the state as whatever based on the operations, but when you want to get the data out of it, you have to measure from the qubit. And the measurement occurs along the z-axis, the up and down. And it will always be a 0 or a 1, depending on whether it goes up or it goes down. And once you measure, you've collapsed the state, and it's gone, and you'd have to reconstruct it from scratch again. And you perform the operations on the qubit using what are called quantum logic gates. The example I put here is the X gate, which is the simplest one to think about. You can think of the X gate on the Bloch sphere as a 180-degree rotation over the x-axis. So if you had a qubit at state 0, like on the left diagram, you apply the X gate, it rotates over x, and then it's down to 1. It's also commonly called the quantum knot operation, because that's basically what it does when it's at the basis state. And there are a lot of quantum gates out there. There are ones for all of the axes rotating over them. There are ones for arbitrary rotation over different axes. And we're really not going to get into all of the different gates that are out there. But the other takeaway that I wanted to mention here, although I'm not going to really go into it in more detail, is that all of these operations can be represented by unitary matrices, which just means that these can all be represented as a matrix that you multiply by your quantum state, and that performs a transform. So all of this can be represented as linear algebra. And I don't really want to get more into it because I'm pretty terrible at linear algebra. But what this also means is that all computation in a quantum computer is reversible. So all of these gates are reversible. So for example, here, if you apply x again, it goes back to its original state. And that holds true for both these simple gates and ones that are more complex, which will come up later when we look at a real example. But we've only looked at when a qubit is at 0 or 1. What happens when it's in the middle? This is called superposition. And it's one of the key differences between a quantum computer and a classical computer, is that you can have a qubit in a state where it's prepared deterministically, but it behaves randomly. And that randomness is inherent to nature. So for example, if we put a qubit at the state there, where the vector is pointing at a +1 on the x-axis, and not any vertical along the z, when you measure this qubit, it'll have a 50-50 chance of being either a 0 or a 1, because you measure along the z-axis, and it'll either collapse up or collapse down, and you'll either get a 0 or a 1. And the gate for putting something in superposition is called the Hadamard gate. The Hadamard gate is basically a rotation of 180 degrees around the x plus the z-axis. I know it's a little abstract. Hopefully this diagram makes it clear. But you apply a Hadamard, let's say it's at the 0 basis state. You rotate over x plus z, which is like a diagonal moving, and then it goes to x plus 1. So this is the Hadamard gate, and it's used for putting things in superposition. The other thing we haven't talked about is the phase, because all of these examples we've been looking at it at either 0 or 1 going up and down. There's another dimension to look at it. If you look at this diagram with the angles, you could be thinking, we were thinking about it with just that theta there as opposed to the phi. There is that other dimension, and we can't use that for actual measurement because we read along the z-axis. But you can encode information in that phase and then use a Hadamard to rotate to get it along the basis state. And you play tricks like this with your quantum programs to perform computation and encode extra information that you couldn't in a traditional binary system. And just to demonstrate the effect that a Hadamard gate has on phase, because everything is reversible, if you had a qubit at the 0 state, you apply a Hadamard to it, you can consider that the 0 plus 1 state, or positive x, on the Bloch sphere. And then you apply a Hadamard again, it goes to 0. But what if the Hadamard's at 1, pointing down? If you rotate across x plus z, it goes minus x, because it's pointing down the other way. So then you can think of that as 0 minus 1. And you can see there the phase is different, which is that minus sign. So then when you apply a Hadamard again, it will rotate down instead of up. And that's just a math way of thinking about the phase instead of trying to conceptualize a three-dimensional sphere in your head when you're applying operations. And the last gate I wanted to talk about is a 2-qubit gate, which is called the controlled NOT gate, or the controlled X gate, which is basically saying if the control qubit is at a 1 state, you just flip the target qubit. It's basically an if, but quantum. So you can see in this example, when the control qubit is at 0, nothing happens to the target. It's the same on either end of the gate. On the bottom one, when it's 1, you just flip it. So the coefficients flip, like a rotation across the x. So if it was at the 0 state, it would be at the 1 state, and vice versa. And then you can put all of this together to build quantum circuits, which is a way of visualizing a quantum program. And in this diagram, you can see all of the gates and all of the bits. And you basically just read it left to right to show the operations that you apply in sequence on a specific qubit. And this is just for showing dependency in operation, not actual timing. And then you can see right there, the last thing on there that I haven't talked about is the measure, which just shows that you're measuring the qubit and reading it to a classical bit, which are the double lines on the bottom. And this is a way you can visualize performing the operations in sequence on qubits to perform computation. And with that, that was all the background I wanted to give. So I wanted to talk about an example problem, something that we can actually solve on a real device today, which is called the Bernstein-Vazirani algorithm. And I know the numbers and the letters are a bit scary, so it's easier to think about it like this. So let's say you have an oracle, and the oracle has a secret bit string, and you don't know what that is. You can ask the oracle a question, which you give it a bit string. It will give you the dot product output. So let's say the secret is all ones. If you give it the bit string 0, 1, 0, 0, you would get back 0, 1, 0, 0. And the goal is to find out what that secret is by only asking with an input bit string. Does that make sense to everyone? Does anyone have any idea how you would solve that with like just a computer today? Brute force? Yeah, and that's actually pretty much the right answer. The ideal way to solve this is you just for loop. So you make a bit mask for each bit in the length of your bit string, and you just loop over it. And you say, okay, so I know you have a bit string of length 4. I'll just give you 1 in each position, and then I'll know whether that's a 1 or a 0 based on the dot product of it. So the ideal case for a classical computer is ON, because you just loop over each bit with a bit mask. But with a quantum oracle, you can do that in one single call to the oracle. And the other thing to call out here is the bottom bit, that temp bit. Remember when I said all operations are reversible? If you have something like this, where you want the secret bit string regardless of what your input is, you'd lose the input information on the output, so you couldn't reverse it. And a way to work around that is by having that extra bit where you can encode the lost information. And that's what that temp bit is for. And the way you construct a quantum oracle is actually really simple. It's just a bunch of C naughts. So in this case, we have 4 qubits, and our secret bit string is 1001. So we just put a C naught where it should be a 1. And I picked 1001 in particular because endianness doesn't matter, it's a palindrome. Because if you put something in the middle and it's not a palindrome, it hurts your head when you start having to think about endianness, just like on a real computer. So this is the implementation, but how does it work? And it uses something called phase kickback, which is, you can kind of think of it like a trick. So let's say we've got 2 qubits, one at 0, one at 1, and we apply a Hadamard to it, so they're put in superposition. You can think of that state, as I was talking about before, as 0 plus 1 and 0 minus 1. You just, the 2 qubits, and those are their states. But it's all linear algebra, so you can just expand it. So it becomes 0, 0, minus 0, 1, plus 1, 0, minus 1, 1. Hope it's not too much like a math lecture. And then if we apply a C naught, the definition of a C naught we had before was if it's 1, you flip it. So we just do that. So what was before now becomes, we just flip it when it's a 1, so it becomes minus 1, 0, plus 1, 1. And then it's just linear algebra again. So you can factor it. And when you factor it, you realize that the phase on that first qubit has flipped. And that's the phase kickback. The phase is kicking back from the target to the control. And then if you were to apply a Hadamard again to it, you would get 1, 1 as your output, which is a bit counterintuitive when you think about it, because if you were thinking in a classical computer, if you had an if condition on a bit, the control would not ever be affected by the output. But it's a bit different in a quantum computer. So when we put everything together, we can use this phase kickback for our oracle. So we just replace the oracle function with our C naught implementation. And then using phase kickback, we'll always get the right answer, or at least hopefully. And now I can actually show you running this on a real quantum computer, or at least hopefully. We'll find out. So is this legible to everyone, especially those in the back? Just give me a thumbs up if it's good. Okay. So this is using Qiskit Terra to define the circuit to start. So we start by outlining our register. So we say we build a quantum register with 4 bits named Q, a temp register of one qubit called temp, and then a classical register of length 4 for our result, which we call res. And we just outline those. Then the next step is to build our oracle function. And we just use a for loop for that. So we define the secret bit string of 1001, or you could put whatever that is in an actual integer. Is that 9, or is my binary to, well, whatever, 1001. We define a circuit called the oracle, and then we just apply CXs when it's 1. So that's what that for loop does. We're just doing a bit shift for each iteration of the loop and saying if it's 1, CX it. And then we build that circuit. Then we build the rest of the circuit. We embed that little oracle bit in the bigger circuit that I drew. So we apply the X gate to the temp bit to make it 1 for phase kickback. Then we apply the Hadamard gates to everything. We add our oracle. We apply the Hadamards again. And then we measure. And we build that circuit. And then we can draw it to verify that, what we just entered in Python matches our expectation of what we want our algorithm to do. And hopefully this looks like what I put in the slides because I copied the code. But so now we have a Python object that represents our circuit that we can run on devices. So to start, we'll run it on a simulator. So we use the error component of Qiskit to say what are our backends available. And there are 3 simulators there. Then They all do different things for looking at different aspects of a quantum computer. We're just going to use the CHASM simulator, which gives us a result, like a number, like is it 1 or 0. You can read the documentation for air to see what the other ones do, but it's not worth getting into. And of course, live demo curse. I run it on the simulator, and it fails. Because of course it does. This was the part that was supposed to work. I'm not going to sit here and debug it for you. I have an example where I show it working. But in the ideal case, the execute command there takes in a circuit and an output device. It will compile the circuit to work with whatever the device specifications are, which in a simulator, it accepts everything. And then it will run it and give you the result. And then I'd be plotting the result here and show that 100% of the time, the histogram shows 1001. In a theoretical case with no noise, it always works. And I'll show you that because I have a notebook saved with the proper answer. I have no idea where this stack trace is coming from. It's looking like it can't spawn the simulator, whatever. Now comes the fun part, where we can run this on a real quantum computer. So I'm going to load my credentials and see which backends are available. We've got 3 devices available. We've got IBM QX4, which is the 5-qubit one from the earlier slide. I've got IBM Q16 Melbourne, which is the 14-qubit device from the slide. And then that's a simulator that runs in a supercomputer. So you can simulate more qubits than what I can run on my laptop, which is apparently 0. But, and then we can use some fancy things for Jupyter notebooks to see the state of these systems. So this is just querying the API. It might take a second because conference Wi-Fi. Come on. Any day. This doesn't bode well. Anyone torrenting on the Wi-Fi? It's Tuesday night back home, but I made sure that the device would be up, not in a maintenance cycle, and they said they gave me priority access, but this isn't even sending anything to the device. This is just, there we go. This is just querying the devices for information. So we can use this to see just an overview of the machines we have access to. So these are the 2 quantum computers that we can run the program on. The one on the left is the 14-qubit one, and you can see the coupling between the qubits, which are the lines. So those are the qubits we can run multi-qubit operations like a CNOT on. And then you can see the coherence times, which are those numbers on the bottom, which tell you how long you have to run operations before you're going to likely lose quantum state and just get random noise out on your output. And you can also see how many jobs are ahead of you waiting in the queue. And now comes the moment of truth to try to run it on one of those devices. And I was told I was given priority access, so I should be able to jump the queue unless someone else with priority access has filled up the queue. So let's see if this works. So it's compiling the job to fit the device to make sure that it matches the coupling map. That's what it says it's doing. Let's see if it lets me jump. The jobs run pretty quickly because you, what? Oh, sorry. The question was, how long do the jobs normally take to run? The answer is they're normally pretty quick. I mean, your coherence time is on the order of tens of microseconds. So each individual run has to fit within that time. Otherwise, you'll just get random noise. But the other thing to consider is because it's such a noisy system and there's no error correction, we could get a wrong answer, which actually, thank you for pointing that out, because something I forgot to mention is that you see that shots argument? We're going to run this experiment 1,024 times. So we can have a plot of what our result is every single time. And of course, yes, there's an admin in the queue in front of me running. So I'm in queue number 94, which is not great because I'm supposed to have priority access and be number 1. What?
There's 103 jobs.
I think it's the number on the left, but luckily I thought this was going to be a problem because I've seen a similar talk and they had the same exact issue. So I saved the results. So we can just scroll down and we can see the simulator results. So we run it 1,024 times in the simulator and we always get the answer 1001, which is what we wanted. It's a bit anticlimactic when you have to go back after it didn't work. But, and then we can run these on the real quantum computers. And the first one I ran on the 5-qubit one because I just sat last night and waited in the queue for my turn. And you can see here, the real device is very noisy. So we ran it 1,024 times, and we only had a 46% chance of getting the right answer when we ran it for real. And then the rest of them were noise. And then I also ran it on the Melbourne device, and it was actually noisier, which makes sense because there are more qubits, there's more things going on, more sources of noise. At least in my head, it makes sense. I'm sure the experimental physicists will disagree with me, but so at least this can hopefully show how you can use a quantum computer to solve at least a hypothetical problem. The oracle problem is not a really good problem. How many times in your day job do you have to go write a program for a function that has a secret number that you can only query with a single bit string and get the dot product? It's very constructed. In fact, it's constructed specifically to show the quantum advantage here. It's constructed to show that you can do in one operation on a quantum computer what would take n operations on a classical computer. But it's not a real world thing. But it hopefully gets you thinking about how you can approach problems differently with a quantum computer to get this kind of speed up. And then I'll go back to my slides to talk a little bit about the role of open source in quantum computing. So the thing that's really interesting is a lot of the tools for dealing with quantum computers are open source. Most of them are licensed under Apache 2, probably for patent reasons, because this is all brand new stuff. And open source is being used to foster collaboration because it's not just one group of people that can build these things. They're incredibly complicated devices that are pushing our understanding of physics. So leveraging open source allows collaboration across multiple institutions and people all over the world to figure out how we can use these devices we have today and also how to push the software of the future to run things on these quantum computers. And the other thing that I find really interesting is that we've learned lessons from the development of classical computers. I remember reading in books about how when classical computers first came out, no one thought anything of software. They just gave it away for free. And then someone realized they could make money and then proprietary software and free software and the whole history. But with quantum computing, we're starting from, you could argue from before day one, especially based on my live demo, that everything is open source to begin with. All of these tools for developing that are open source. So if you're interested in this field, even though the technology isn't the most mature yet, you can still experiment with it, see how everything works, learn about it. I don't have a background in experimental physics. I worked on cloud software before I started working on this, but because it's all open source, I was able to dig in and at least pick up a little bit of knowledge, or at least I hope I have. And the other thing that I find really awesome is just the sheer number of tools. The longer I've worked in this space, the more and more open source tools I've seen. I highlighted a few of the bigger names if you search for open source quantum computing, just as links there. A lot of them are actually pretty similar to QuizKit. They're just developed by different companies that are building quantum computers. There are exceptions there. Project Q there is one from Microsoft, which is called Q#, and it's their approach to a quantum programming language, which is like C# and needs Visual Studio, and I never touch it. But you can just do a search. I typed that topic into GitHub, and there were over 300 projects that have tagged themselves as being quantum computing. And this is day one, basically. And it's really, really exciting to me to see that everyone is embracing open source for a field that's just getting started. So to bring this all together, I just want to say that a lot of people ask, why are we developing quantum computers? And it's not to replace classical computers, at least anytime soon. It's to solve the problems we can't solve with the classical computer. There are a lot of problems that are very difficult or next to impossible to solve with a classical computer unless you have infinite time or infinite resources. And classical computing, at least theoretically, shows us that we can solve these problems with a quantum computer. So developing this technology and experimenting with it is to try to solve problems we can't solve today. But it's still very early for the technology. The key takeaway I want everyone to have, though, is that quantum computing isn't just in a lab today. It's accessible to everyone. Everyone can sign up and submit jobs to a quantum computer. And all of the software to do that is open source. And I think that's really cool. So with that, I put up some links where these slides are, some more information about QuizKit. That link at the bottom is QuizKit tutorials. It's a bunch of IPython notebooks that explain concepts in quantum computing using QuizKit, and basically kind of like what my demo was supposed to be. But different things that are a lot more advanced and go into all of the information. And then also, if anyone is interested and wants to sign up, you can use that quantum experience link to sign up to get access to the quantum computers and submit jobs and experiment and play around with it. So with that, that's all I had for prepared material. Are there any questions? So we've got 2 questions there, and the poor runner is going to...
Are they still developing like new quantum algorithms, and has open source helped to make new innovations?
So there are still new algorithms under development. That's a field of very heavy research. I'd say that's more the field of academic research right now. So there's published papers on the topic, and that's where the developments in that are happening. There are libraries for established quantum algorithms that exist today that are open source. The Aqua thing that I talked about earlier, that's an example of that. But because quantum computing is so new and so different, I don't think open source has had time to show its true advantage in collaboration on developing new algorithms yet, because not enough people understand how to program it, except for people who have PhDs in math and quantum information theory.
Just wonder, any people out there started using quantum computing at the moment for real life or cases?
You mean for like a business use case, or?
Yeah.
Okay. I'm not sure what I'm allowed to talk about. There are people using it, but it's mostly like research, trying to figure out how they will use the devices in the future. There are promising fields like quantum chemistry, where this is being looked at and actively researched to solve real problems.
In the financial world, there are people trying to do
Yes, and as he said, in the financial world, there are also people trying to use quantum computing. There's a guy been right there patiently waiting.
Which language is used to control the hardware part of quantum computer? Is it still assembly?
So it's a bit more complicated than just a language, because all of these operations are being performed by microwave pulses. It's like interfacing with basically like lab equipment to generate like arbitrary waveform generators to send the pulses. So there's a software stack that translates from what QuizKit sends to those.
in your definition of quantum oracle, you used res as one of argument. Actually, it's not used in the oracle, right?
Sorry?
Can you show the definition of quantum oracle? No, the code.
Oh, the code.
Yeah. It's above, I think. Below. So why you use this res?
The res?
Oracle? Yeah. It's not used in the oracle. It's just transferred.
So those are the classical bits, the classical register where we store the results.
Yes, but it's only used later in the code. If you see the
because the oracle we're defining as its own function. So we define a circuit object for just that function, and then we build a separate circuit object, which is like the bigger circuit, and we embed that in the smaller one. So it's like a combination of, well, you can add circuits together and it'll just add the operations to the end of the current of the circuit you're working with. So this line, BV plus Oracle, takes the operations we defined in that Oracle circuit object and embeds it in this BV object.
Okay.
Does that make sense?
Yeah, kind of. And the second question, is there any research to reduce the noise in the hardware?
Yes,
qubits?
lots and lots of research on that.
By the way, kudos to the runner. I'm a professional ignorant, so I ask questions for a living. You say that you have a... Can you share the journey? You say that you came from the cloud computing world. I mean, I recognize Hadamard from my days of calculus, but that's 100 years old or something like that. If I want to employ someone to explore the basics of quantum, which would be the timeline that I should give to someone to say, okay, if I want to go, I don't know, go into business, into the financial world, is a 6 months project, is a 6 years project? Do we need to know theoretical physics? Give us just a totally high level comment.
I mean, I understand this talk, and I've been working in this since August. I transferred departments from working on cloud computing to this back in the beginning of August. I don't pretend to understand all the maths, and I feel for myself that's a limitation when trying to develop my own algorithms. I can parrot one from a textbook or a paper from 1993, but I can't develop my own. I don't have an answer for trying what the timeline would be for trying for that skill set, but for picking up the Python and learning the basics of how circuits work and that kind of stuff, I was able to pick it up in a few months personally.
Well, I have more or less a theoretical question about the complexity classes involved here. What's the relationship between classical algorithms and these quantum algorithms? I know an example from the 1960s where you know register machines, and there are variants like vector machines where you can encode it arbitrarily many bits in one register and have AND and OR operations, and some algorithms are running faster there, as in a classical machine or in a classical Turing machine.
Yeah.
And it would be interesting to know the relationship, what's the potential speed up by this quantum and related to classical algorithms?
Yeah, I'm not sure I'm able to answer that. I did have a backup slide that I put together about complexity, which was something I didn't want to get into, which is the other principle in quantum mechanics that makes quantum computing unique, which is entanglement, which is you can have two bits that behave independently random but correlated. And that leads to an exponential growth in complexity as the number of entangled qubits grows. But I don't think that really answers your question.
Well, it's an indicator.
Yeah.
It's an indicator.
Okay. Well,
Well, as practical experiences was an indicator. Do you have one? Simulator. If you compare on the real machine and simulation, what's the factor between? Yes, of course, but
yeah.
Sorry, guys, I have to cut it short. We're just out of time. But could I get you all to please give a round of applause for Matthew Kranish?